Welcome to Empowered Learning. This video will be about continuity and how we define continuity in a first-year calculus course in terms of limits. Specifically, we're going to talk about the definition of continuity in terms of limits, just like I said before. We will also talk about the definition of what a discontinuity is, and we'll give explicit examples of the different types of discontinuities we will see. In addition to that, you will see how we will actually express each discontinuity in terms of a limit as well. And we're also going to go over some basic theorems that follow from the definition of continuity and give some examples on exercising those theorems. I also have here in my list that we will cover the intermediate value theorem, but I won't be covering that topic in this video because I actually have a separate video on the intermediate value theorem by itself. So let's go ahead and look at what the definition of continuity actually is in terms of limits, and let's try to make some sense of it. So the definition, continuity of a function f at some single number x equals a. So I want to make sure that we understand that I'm only talking about continuity of a function at a single point at this particular time. We will build upon that and eventually talk about continuity of a function for several points in succession or an interval of x values or whatever later. But for right now, we're just talking about what do we mean when we say continuity of a function at a particular point or at a single x value. So we consider a function to be continuous at a number x equals a if all of the three characteristics of this function f are true. So number one, f of a, meaning f evaluated at the x value a, is defined. Okay, so what that means is we know that a is in the domain of the function. So we plug in real number a into the function and we get out a real number. Okay. Number two, we know that the limit of this particular function f of x as x approaches a from both the left and the right exists. Now, what does that mean? It just means that if we evaluate the limit of this function at x equals a, then it's going to equal some real number. Okay. So first we have to know for the function that we're dealing with and the x value that we are evaluating the behavior by, that particular function at that x value is going to produce a y value that's a real number. The limit is going to equal to some real number, meaning that the limit has to exist. And the third thing is that the number that we get for the real number here and the number that we get for the real number when we evaluate the limit have to both be equal to each other. Okay, so put this in another way, criterion number one results has to equal criterion number two results. And so sometimes what I've shown you here is called the test for continuity criterion, but really what it is just the definition of continuity. So there's three things that let us know that a function is continuous at a particular x value. Number one, that function's defined at that x value, the limit exists at that x value, and that the real number values for the limit and what the y value is for that function are the same. If we have all three of those, we can say that our function is continuous at that particular x value. Now, sometimes it is beneficial for us to talk about continuity only from the right and only from the left. And if you've watched my video on one-sided limits and infinite limits, you'll know that this whole left-sided and right-sided thing with the limits really goes good with functions like logarithms, functions that have vertical asymptotes in them, and functions where the domain stops abruptly. And an example of that would be square root of x. So here, this should be a plus, by the way. So it's looking kind of funny. We say that a function f is continuous coming from the right of x equals a if the limit as x approaches a from the right of that function equals this real number value. And of course, limit of the function as x approaches a from the left. If that equals to f of a, then we say that the function is continuous from the left. So basically what this says is that it satisfies all three of these conditions here, but the only difference is that we're only considering the limit looking from one side of our x value versus both sides. All right, so now what we need to do, since we've actually defined what continuity is, we need to talk about what continuity is not, okay? And we're going to talk about that a little bit later, but let's first make sure that we know when we talk about continuity, what that actually looks like, okay? So we're first going to talk about, when I say a function is continuous, what are the various ways that could look? And then we're going to go into what will it not look like, okay? So here we see that we have a function f is continuous on an interval if and only if every number in that interval is in the domain of that function f. Meaning every x value that you choose, you plug it into that function, you get a corresponding y value out. Or every x value that you have has a corresponding y value to go with it. If f is defined only on one side of an endpoint of the interval, we understand continuous at the endpoint to mean continuous from the right or continuous from the left, depending upon if the function's right side or the left side. Okay. Now, we have various definitions of continuity for the following cases. And so here's me trying to attempt to show you all the different ways we could have continuity. So what you're seeing here is the traditional visualization of what continuity is of a function at a single point here, okay? And so if you notice this first one here, we have our point, and this function is both continuous as x approaches a from the right as well as from the left, and what the limit of this function is the same as what f of a is, okay? Now, if a function is continuous only from the right, it's going to look like this. Now, notice here that the defined point on the graph at x equals a is on the right piece of this function, okay? Continuity from the left, kind of the same thing, but where the function is actually defined is on the left piece of the function in regards to x equals a. And then if we have continuity on an interval, notice that here the defined points here are on this particular interval, and therefore we say that the function is continuous everywhere in between x equals x sub 1 and x sub 2. We don't necessarily say that the function is continuous at x equals 1 because of the fact that it's not continuous both on the left and on the right, okay, in both of these cases here. So we're not going to say that x is continuous at x equals -1, but we can say that this function is continuous at x equals 1 coming from the right, and this function is continuous at x equals x sub 2 from the left, okay? All right, so now that we've looked at some examples visually of what continuity does look like, we need to know, well, what does continuity not look like? Meaning we need to see some examples of some discontinuities. And so I have a list of those discontinuities here. This is not an entire list, but this gives you a good idea of what you need to consider. Of course, first, you have a hole in your graph. This is also known as a removable discontinuity or removable discontinuity, depending upon how you want to say the word. And basically what this shows you here is that your function is undefined at a certain value here. So what we're showing here is that f of 4 is undefined. And of course, if you have a situation like this, we know that the limit of this function as x approaches 4 from both the left and the right will exist, and it'll be, whatever real number this is here, but the function itself is not defined at x equals 4 in this example. Anytime we have a break or a gap, the function is not going to be continuous for all these numbers in between 1 and 2 here. And even with this point, it will only be continuous coming from the right of 2. Okay. We also see here we have a jump discontinuity. And of course, we have several different types of jump discontinuities. This is just one type. Okay. We can also have another jump discontinuity to where the graph could be something like this. Let me draw it right quick. So let's say we have a hole here, and we have, let's say something like this where it comes down like that. We could have something like that, or this could switch. This could be the hole, and it could be like this as well. Okay. And so one of the things that we'll see, and I'll make another video on this, on interpreting limits, is that a jump discontinuity that is like this one, from a limit perspective, is different than a jump discontinuity like this. And so based upon the type of jump discontinuity it is, the statements that we have to write in terms of limits will look differently. Okay. At the end of a domain, so this is a function that stops abruptly at x equals 10. This function is not considered to be continuous at x equals 10 if we're looking at it both on the left and on the right of 10. Now, this function is considered to be continuous as x approaches 10 only from the left. So if we were looking at this left-sided, we would say that this function is continuous only from the left. But if we just said, hey, is that function continuous at x equals 10, and don't specify that we're talking about from the left side, then we would have to say, no, it is not. Of course, from pre-cal, we know about vertical asymptotes. And of course, this is a discontinuity here. And we know in this case that the limit of this particular function as x approaches 2 coming from either the left or the right is going to end up being infinity. Okay? And of course, any function whose limit, when we evaluate it at a particular x value and it ends up being positive or negative infinity, even though it may be the best way to describe the behavior, the limit does not exist in this case. And since that limit won't exist in this case, that means that's translating over here that this function will not be continuous at x equals 2. All right, so the next thing that we're going to do, now that we have seen what continuity looks like graphically, as well as what it does not look like graphically, is we want to go over those 3 criteria again on what does it take for a function to be continuous at a particular x value or at a particular point. And we want to see what does it look like if we violated at least one of those criteria each. Okay. So of course, the first criteria is f of a is defined. The second is that the limit as x approaches a of f of x exists, which means that it ends up equaling a real number. And the third one is that the result for the limit has to be equal to the result for the function, the y value of the function at x equals a. So we're going to look at what does it look like if we purposely violate one of these criterion at a time, so that we can see if a function is not continuous, how each criterion makes that happen. So if we look at this graph of this function f I've made up, and we look at a, we see here we have a removable discontinuity, better known as a hole. Okay. Now, the reason why this function will not be continuous at x equals -1 is because f of a is not defined. So if we violated criterion number 1 only, that would be an example of what that would look like. Okay. Now, example B here is an example of what could happen when the limit of the function as x approaches some value a does not exist. In this case, when x is equal to 1, we see that the behavior of this function as x approaches 1 from the left is different than the behavior of this function as it approaches x equals 1 from the right. Okay, and here behavior is that the y values that it approaches is way up here, whereas on the right of x equals 1, the y values that it's approaching is here. Okay, so because of that, we see how example 2 is, criterion number 2 is violated. Notice that criterion number 1 still holds because at x equals 1, I do have a defined point on this graph. Okay, but criterion number 2 is not holding. Now, if we look at criterion number 3 here, or example C, notice that example C here, we do have a defined point at x equals 3. So criterion number 1 is satisfied. Okay. The limit of this function as x approaches 3 from both the left and the right are going to approach whatever y value this is here. So criterion number 2 is satisfied. But we see that the y value for this point and the limit, or the y value that this function is acting like it's trying to approach, are different. And so for that reason, we see that criterion number 3 is violated. And so that's an example of what it would look like if we were to violate that particular criterion. And so here, what that looks like notation-wise, we see here that the limit of our function, which was criterion number 2, is not equal to what f of a is, or in this case, f of 3, and that would be criterion number 1. So symbols-wise or notation-wise, that is what that would look like. All right. So now we have a very good idea, at least visually and as well as through definitions, what continuity is, what it looks like, as well as some examples of what continuity is not. And we've also said with that definition, if we were to take that definition and break it down into each of its 3 criteria, we can see how if we violated one of those criteria at a time, what that would look like. Now, I wanted to take a step back here so that we can just kind of think about what continuity actually is from a layman's point of view. So remember that when you first learned about continuity, what your algebra instructor probably told you is that, hey, functions that are continuous, you can draw them with your pencil or pen without having to pick it up for, the values of x where it's continuous for. So if I was to draw a function like this, then all the x values from this first point here all the way to this last point here, I would say that this particular function is continuous from x equals a to x equals b, and that would be everything in between. If I put arrows on here like this, then my function would be continuous for all real numbers. Okay. Now, from a layman's point of view, again, if I'm able to draw a function with a pencil or a pen and not have to pick up that pencil or pen at any given time, then what I've drawn is at least a piece of that function that's continuous for the x values that you drew it for. Okay. So just keep that in mind. We're trying to formally define what continuity is in terms of limits, but it still always goes back to that very simple way of thinking about it. If I can take my function, draw it with a pencil or pen, and I have to pick up my pencil or pen while I'm drawing that particular function, then whatever I've drawn is going to be continuous for that portion of the function. So now we're going to look at theorems as a direct consequence of the continuity definition. So these are the basic facts that fall out as a result of defining continuity in terms of limits. And so here, now that we have properly defined what continuity is and what it is not, we now ask ourselves if we can know whether some function f is going to be continuous if f formed from other functions assuming those parent functions are continuous over some interval of x values as well. Okay. So in other words, if I have two or more functions and I want to create new functions from old functions, how am I going to tell whether those new functions are continuous or not? Okay. And in order to do that, I would have to know something about the two or more functions that I'm actually trying to form new functions from to be able to give that result. Now, it turns out that the following 5 theorems that I'm going to state here identify when and under what conditions we can determine if such functions are continuous, meaning the new functions that we are creating from old functions, we'll know under what conditions we can determine they are going to be continuous or not. Okay. Now, I'm going to state these particular theorems without proof, and we'll use these theorems along with a variety of definitions of continuity to work several examples afterwards. Okay. Now, some of these definitions are these theorems rather, are going to be very common sense. Okay. And really they are here just to make sure that you kind of log them and say, yep, I was thinking that anyway, aware of it, going to move on. There are going to be other theorems that are not going to be so, I guess a better way to put it, I guess a good way to put it would be they're not going to be so easy to understand. Okay. I'm going to introduce them now just so that you kind of get a general understanding of what those theorems are. But we will actually start to use those theorems much later on in your first year calculus course. So the last 2 theorems I'm going to introduce to you before we get into the examples will actually be examples that you will probably see when you start to learn about L'Hopital's rule, because that's one of the places where it's really used a lot. Okay. All right. So let's just get to the theorems here. So theorem number 1, continuous via linear transformation. So if I have 2 functions that I know of, and I know that they are continuous, and I have these 2 constants a and c, then I know that the following new functions that I can create from these old functions will also be continuous. Okay. So if I do the sum of those 2 functions, the difference, the product, and the quotient of those 2 functions, as long as I don't have this particular function here being evaluated at some value a that makes it 0, and a constant multiple of any one of those functions. If I know that f and g are 2 functions that are continuous, and I have a and c that are constants, then I know that all these functions are also going to be continuous as well. Okay. Theorem number 2. Any polynomial function is continuous for all real numbers. Okay. And we know that because any polynomial function, if we plug in a real number x value into it, we get a real number y value out. And of course, for any polynomial, all 3 of the criteria that we have for continuity, all that will be satisfied. Now, a rational function is a function, I basically call it a polynomial fraction, but a rational function is going to be continuous for all the x values in its domain. Now, specifically for a rational function, remember that rational functions only have 2 types of discontinuities. Okay. And those discontinuities are vertical asymptotes, and they are removable discontinuities, better known as holes. So as long as you are at an x value in a rational function for where you do not have a vertical asymptote or a hole, that function will be continuous on those interval of x values. All right, so theorem number 3 is going to be a build on of theorem number 2. So with theorem number 2, we've said that, hey, we understand that if we're dealing with a polynomial function or a rational function, polynomial functions are going to be continuous for all real numbers. Rational ones will be continuous for everywhere in this domain. Well, theorem number 3 says, all right, this concept could actually extend as far as functions being continuous everywhere in their domain for all of the following functions. Okay, and so that including polynomials and rational functions, we also got trig functions, exponential functions, inverse trig functions, logarithmic functions, and nth root functions. Okay, and these are better known as radical functions. So stuff like cube root of x, fifth root of x raised to the 5/3, stuff like that. Okay, so again, these first three theorems here just basically say, all right, well, most of the functions that we're dealing with, if I know something about, let's say, two or more specific ones, and I want to create new functions from them, I can pretty much say that, hey, they're going to be continuous everywhere in its domain. Now, the last two theorems are theorems that deal with defining continuity in terms of a composite function. And so we have one theorem that looks at continuity of a composite function looking from the outside of the function to the inside of it. And the other theorem, which will be the fifth one, will be just the reverse. It'll be looking from the inside going to the outside. Now, theorem number 4, what it says here is that if we have some function f that is continuous at some real number b, so in other words, if I was to say, so we got some function here, it's continuous at some real number b. So let's say x approaches b. So we got a situation like this, okay? And on top of that, we have the limit of some function g as g approaches a equals this particular value here. Then what we can say is that if f is a function that is composed of g, meaning that g is the function that's stuffed on the inside of it, then we can say that the limit of this composition function here is just going to be f of b, okay? And so if we look at this from a practical sense, what we're really saying is the following, okay? If I have a composite function and I want to take the limit of it as x approaches a, and I know that the limit of the inside function for my composite function as x approaches a equals this value here, then I could take this limit operator and I can slide it on the in the composite function to on the inside function, okay? And so essentially what I'm doing is I'm taking the limit of the inside function, figuring out what that answer is, and then after that, taking that answer and evaluating the function f by that result, okay? So again, theorem number 4 just basically says, if you got a composition function and you know that the inside function, if you took the limit of it as x approaches a and it's going to equal to some other number b, then you can basically take that limit operator, slide it inside the composition function to where you just evaluate the inside function first at that x value, and then take that result and evaluate the outside function. Now, theorem number 5 is kind of saying the same thing, but in reverse, okay? So it's saying that if g is continuous at some real number a, and f is continuous at some number g of a, then we know that the composite function f of g of x is going to be continuous at x equals a. So notice here, what this is saying is that we're looking at the inside function, because we're still assuming that our composition function looks like this. So if I'm looking at the inside function, and I was to say the limit of it at x approaches a is going to equal some real number, and we'll just call it g of a. And we know that f is also continuous at g of a. Then, of course, then we know that the composite function is going to be continuous at x equals a. Now, again, these last two examples here, we don't see a lot until we get later on into a first year calculus course. So I wouldn't necessarily worry about them now. If you're watching the videos that I make here for your primary learning, then when we get to a point in the course to where we actually use these theorems, I will go back to these notes here, and I will let you know that, hey, we're able to do such and such in these types of problems because of these two theorems here. So I don't want you to worry about it too much, but I do want you to at least be aware that we do have some limit theorems or some rules on how we deal with the limit of a composition function. All right, so now what we're going to do is exercise what we've learned here by doing some examples. And so this will be the first one. So the goal of this particular example is to look at this function and be able to determine where this function has discontinuities, or put another way, tell me where the function is not continuous. We want to know whether the function is going to be considered to be continuous to the left or to the right. And we want to know if the function is not continuous, why is that? And what we want to do is refer to it in terms of the three criteria that we have for continuity of a particular function at a particular x value. So I'm going to briefly write those up here again, just so that we know. And so criterion number one, f of a is defined. Number two, the limit of some function as x approaches a exists, meaning that it equals to some real number, and we're just calling it L. And three, we know that the result from 2 has to be equal to the result of 1, meaning that the value of L here and f of a have to be the same. So you could also say it like that. So f of a has to equal L, if you want to say it like that. So first, if we look at our graph of f of x here, we can easily see that we have a discontinuity here because we have a hole. So that'll be x equals -6. We have one here at x equals -4 because we have a jump discontinuity. We have one here at 2, same thing, jump discontinuity. And it may not be as obvious, but we do have one at x equals 4 as well, because the way in which this acts on the left side of x equals 4, it acts like we have a vertical asymptote, and on the right side, the graph abruptly starts. So now that we know that, let's go back and see, let's go back and see if our function is actually continuous only on the right, only on the left, or neither. So for our first location, which is at x equals -6, because we do not have a defined point here at all, we can't say that the function is going to be continuous on the left or right. So this would have to be a neither case. Okay. If we move on to the location x equals -4, we do have a defined point here. And if we look at it, it is on the left piece of our function in reference to x equals -4. So this function will be considered to be continuous to the left at the location x equals -4. At x equals 2, we see since the defined point is here, the function will be considered to be continuous from the right at x equals 2. And then, of course, here at x equals 4, this graph goes down to -infinity on the left, but it is equal to, is at the point 4, 1 on the right. So this function at x equals 4 would be continuous coming from the right. All right, so the last thing that we'll do is go back to each location and we'll talk about why the function is not continuous, okay? So if you remember, we said here that this function is not defined at x equals -6, and that's criterion number 1. So why is it, why we have a discontinuity there? Because of criterion number 1 is violated this is not defined, okay? All right, so let's look at the location x equals -4. Here we see that criterion number 2 is violated, and that will be because the limit does not exist. So the limit as x approaches -4 of our function here does not exist case, because the behavior coming from the left isn't the same as the behavior coming from the right. Meaning the y values that this function approaches as x approaches -4 on the left is not the same as the y values that it approaches as x approaches -4 from the right. Now, anytime criterion number 1 or number 2 is violated, by default, number 3 will be violated as well, okay? And so I'm not really worried about stating number 3 on these, just because, hey, if 1 and or 2 are violated, of course 3 is automatically going to be violated. Now, at location x equals 2, we see here that the function is defined on the right, but reason being, again, same as it was for the location at x equals -4, limit doesn't exist at that particular x value. All right, and for this last location here, we see that the problem here also is criterion number 2, because the limit as x approaches 4 from both the left and the right will not exist. Reason being, the limit from the left approaches -infinity. Limit from the right will approach 1, okay? And since those behaviors are not approaching the same y value, we know that, hey, that's why it's not continuous. Okay, so now what we want to do is take a step back for a second and look at this function, and let's review how do we actually evaluate the limit of a function whenever we have a graph of it, and we just want to evaluate what the limits are or study some of the properties of this particular function. Now, the reason I'm doing this particular exercise is that since we have now learned a new concept, and we've learned that concept in terms of limits, we need to not forget what we need to do to be able to just evaluate the limit of a function in general, okay? So I'm trying to do my best here to make sure that you keep the concept of what evaluating the limit of a function is when you have a graph of a function versus you are talking about the continuity of a function at a particular x value. And so it's been my experience with students that once I introduce this concept of continuity, they start to either forget or get mixed up the whole concept of evaluating the limit of a function with the whole concept of continuity. So I'm doing this just as a way to make sure that we keep those two different things straight in our mind. Okay, so for our first limit here, we want to find out what is the limit or the behavior of this function as x approaches -6. And of course, since we don't have a plus or minus in the exponent, that means we're looking at it from both the left and the right. So the limit of this function as x approaches 6 from both the left and the right is going to approach a y value of 3. And of course, even though the function is not defined at x equals -6, it still is acting like it's approaching a y value of 3. And so we'll write that as our answer. Next, we'll find out the behavior of this function as x approaches -4 from both the left and the right. And you see here, since the limit coming from the left does not approach the same y values as it does from the right of x equals -4, this would be a does not exist case. So if we look here at x equals 2, if we see that the behavior of this function as x approaches 2 coming from the right, it is approaching a y value of -4. If we look at the same location and look at the behavior of the function as x approaches 2 from the left of x equals 2, then it's approaching a y value of 1. At x equals 4, if we look at the behavior of this function as x approaches 4 from both the left and the right, we see that on the left it's going to -infinity, on the right it's going to 1, but on left and right, since it's not the same, this would be a does not exist case. Now, of course, this limit, this is same as here, but we're looking at the behavior as x approaches 4 from the right, so we know that that's going towards 1, and this is asking the behavior from the left of x equals -4, that goes down to -infinity. And then lastly here, the limit of f of x as x approaches 2, so that's here coming from both the left and the right. Since coming from the left, it approaches 1, from the right it approaches -4, that would be a does not exist case because of the fact that the limit from both the left and the right do not approach the same y values. All right, so moving on to our next example here, we see that we want to look at these two piecewise functions, and we want to explain why our function has a discontinuity at the given value of a that we're asked to look at. And so what we want to do is basically describe what's happening and give the criterion that fails in the definition of continuity. Okay, so for this particular case, we have this piecewise function. Now, of course, I've drawn a graph for it, and just from a layman's point of view, we have a jump discontinuity here. Okay, and so of course it's not continuous because we have a jump discontinuity. Now, from a formal perspective, what happens here is criterion number 2 is violated, meaning that the limit as x approaches 0 of this particular function does not exist. Okay, and so that is the reason why this particular function will not be continuous at x equals 0 from a formal perspective. Now, for example B, have our piecewise function. We've drawn it here, and we see at x equals 3, and we just say a is 3 here. The problem here is that criterion number 3 is violated, which is the limit of our function as x approaches 3 from both the left and the right does not equal the same as what f of 3 is. Okay, and to be specific about it, f of 3 is equal to 6, but the limit of our function as x approaches 3 from both the left and the right is equal to 7. Okay? And so because of the fact that f of 3 and the limit as x approaches 3 from both the left, the limit of the function as x approaches 3 from both the left and the right aren't the same, then this function can't be continuous. Now, of course, from a layman's point of view, again, this is another jump discontinuity. Okay, and notice how this jump discontinuity is different from that one. Still, same situation here, where it's still not continuous, but here we see criterion number 2 is violated for that type of discontinuity, where here criterion number 3 is violated for this other type of discontinuity. All right, so let's look at this last example here on this page. And we want to use the theorems that we talked about earlier in this particular video, or in these lecture notes, to explain why our function g of t, which is natural log of t to the fourth minus 1, is continuous at every number in its domain. Okay. Now, we're going to take a step back to those theorems to actually see what it is that this particular problem is trying to get us to do. And then afterwards, what we need to do is actually find out the values of t where this function is continuous. So looking back at the theorems that we talked about, if you see here, theorem number 3, after we had talked about if we know we got two functions and we know they're continuous, then we can form the sum, difference, product, and quotient and constant multiple of any one of those functions. That would also be continuous. And of course, with polynomials and rational functions, then of course the other type of functions would be, in addition to the polynomial and rational ones, would be our trig, exponentials, logarithmic, inverse trig, and radical or nth root functions. Now, for the example that we're going to do, we have a function g of t is equal to natural log of t to the 4 minus 1. Okay. So here, this would go along the lines of really being a composite function here, where the outside function is a logarithm, the inside function is a polynomial. Okay. Now, we're not going to use theorem number 4, theorem number 5 to sort of prove that, but we know that from theorem number 3, since this is really natural log of something, that we know that as long as we can find the domain of this particular function, then we'll know all the values of t for where it is continuous at. And so that's where we're actually going to start trying to figure out, hey, for what values of t is this function continuous? Well, to answer that question, we have to find the domain of this function. Okay, so to find the domain of our function g of t here, we have to remember a few things. So in general, if I have natural log of something, okay, doesn't matter what it is, or log base a, doesn't matter what a is of whatever this something is, we know that it always has to be greater than 0. Okay, and we know that because of how a basic logarithmic graph looks like that, where we have vertical asymptote here at x equals 0. Okay. So not the best looking graph of a logarithm, but that's the general idea. So here, what that means is, since we have t to the 4th minus 1, that is inside our logarithm, to find the domain of g of t, we would have to set t to the 4 minus 1 to be greater than 0. Okay. Now, in order to solve this inequality correctly, there's two approaches that we can take. The approach that is a little bit more conceptual is we just need to draw a graph of what this particular inequality statement is trying to communicate. Okay. And so from a graphical perspective, this inequality statement here says, tell me all the values of t when the graph of t to the 4 minus 1 is strictly above the x-axis. So t to the minus 4 looks a lot like t squared. It just rises higher. So of course, we know t squared just looks like a parabola. So that means t to the 4 is going to look the same. So where t squared would look like this, t to the 4 would look like that. So if I was to draw what t to the 4 minus 1 would look like, it would essentially just be this. Okay. And of course, these x-intercepts here would be minus 1 and 1, because of course, if I plugged in 1 or minus 1 in for t, that would give me 0 as an outcome. Now, what I'm interested in is the values of t for this function for where the graph is strictly above the x-axis, okay? And that happens for all of these values here, values that are greater than 1, and all of these values here, where the values are less than negative 1, okay? And I'm going to move that negative 1 out the way because we don't want that to be confused with the other one that we had. So this -1 belongs down here, okay? So we can see just from a graphical perspective of understanding conceptually what this particular inequality statement is saying, we can see here that t is going to be all values of, that the domain is going to be all values of t that are either less than -1 or greater than +1, okay? Now, if we looked at this from more of a computational perspective, we would have to do the test interval method for this, which means that I would have to look at t to the 4 minus 1, and I would have to factor it like this. And then, of course, t squared minus 1 would be t minus 1 times t plus 1. And this would be t squared plus 1 here, greater than 0. And then the test interval method says we need to identify where our x-intercepts are, in this case t-intercepts. And this would be at -1 and 1. Notice that t squared plus 1 does not give us any real number t-intercepts because the only values of t that would make this go to 0 would be a -1, sorry, not -1, it would be a I or -I, okay? And of course those are complex numbers and we don't consider that in these types of problems. So once we have our t-intercepts here, notice that we want values of t for where it's strictly above the x-axis, so we exclude these t-intercepts from being in our answers, and then we say let this be f of t, and we just plug in values that are in between these intervals here, and we look for the intervals where we end up getting a positive result, okay? So here if we have f of, let's say in this interval, and I'll say from -infinity to -1, we got 1 to -1 to 1 here, and we have 1 to infinity. So in this first interval here, I have a number -2 I can plug in. If I was to plug in -2 in here, then let's say I had -2 here, -2 here, and -2 here. This first term would end up being negative. Second term end up being negative. The third term is always going to be positive no matter what, because t squared minus 1, as long as you're plugging in real numbers, always going to be positive. So we see that the result that we have here is going to be positive number. It's positive, and that's why we picked that one, because positive means that those t values correspond to y values that are above the x-axis. If we did the same thing with the next interval, we can choose the value of 0. So let's choose that. And of course, if I was to plug in 0 here instead, then I would get a -1. If I was to plug in 0 here, I would get a -1, which would be a negative value, +1, which would be a positive value. And of course, the third one would always be positive. So we get negative number there. And that corresponds to this graph being below the x-axis here. We don't want that. And then of course, for the last one, we could pick the number 2 in this interval. And if I was to plug in the number 2 here, number 2 there, number 2 there, then I would have positive, positive, and positive numbers all being multiplied times each other. I'll get positive. And of course, that is why we pick that interval as well. And that corresponds to the graph being above the x-axis there. So if you're asked to say, hey, for what values of t is this particular function going to be continuous, these are the two ways that you would actually do that problem, okay? Now, I'm making a point to kind of review some pre-cal here, because of the fact that when most students that I know of try this problem initially, they kind of approach it wrong and they miss some things. And I'm going to show you exactly what I'm talking about here. So my experience has been that most students, when they try to work out this particular inequality here, what they'll try to do is treat this as if it is a linear inequality and just add 1 to both sides, and then end up trying to take the 4th root of both sides here. And then this will be t, and that'll just be greater than 1. And they'll say, hey, t has to be greater than 1, okay? And in doing that, you get some of the actual answer, but you don't get all of it, okay? And so remember, we found from this that we actually had an interval of values that was all values less than 1, as well as numbers that are greater than 1. So here, trying to solve this polynomial inequality like a linear inequality is only going to give you this result here. But because you didn't solve it with thinking about what does the graph of this particular function looks like in line, you totally miss this portion, okay? And so that was the reason why I took the approach of either just looking at what the graph of this looked like to begin with, or taking into account that when I factor this, it's going to look like that. Okay, so for our last example, what we're going to do is look at a piecewise function, actually a family of piecewise functions. And what we're going to do is find out values a and b, and we're assuming that they're real numbers, so that this particular piecewise function will be a continuous function for all real numbers. So before we actually start with working this problem, let's sort of understand why this problem is even important, okay? Now, if we look at this piecewise function, since we don't know what a and b are, this could be anything. And so because of that, the combination of a and b values that we could use could really come up with a myriad of possibilities of what this piecewise function would look like. Now, without loss of generality here, let's say that this particular function, if we were looking at it graph-wise, would look something like this, okay? And so we see most of the action is happening, let's say, near x equals 2 and x equals 3. So I'm going to sort of adjust what this graph's going to look like here. Try to mirror that. So we'll kind of do more like this. Well, here I'll do 2 and here I'll do 3. So let's say for this first piece here, of course, if we factor this out, this would be x minus 2 times x plus 2. So the result of this would, really be like x plus 2. So it's going to look like a line with a positive slope. And it's going to look like that for values of x that are less than 2. Okay, so just to kind of guess what it may look like, let's say if I plug in 2 into here, 2 plus 2 is 4. So this line is going to look something like this, okay? Now, ax squared minus bx plus 3, this is a parabola. Since I don't know what a and b are, I'm not sure if my parabola is going to be one that's going to be like up here, or if it'll be down here or way down here. I have no idea, okay? So I'm just going to take a guess here and say that my parabola is going to be here. They'll start at this point and it'll do something like this. Okay, and we'll have an open circle there because we have less than or equal to here and we have less than there. This particular piece looks like a line again, and remember a and b are just constants, so whatever this is going to be a real number. But since the slope here is 2, we know that it's going to be a line with a positive slope, so it's going to look something like this. But of course it's going to start when x is equal to 3, and let's just say for example that the line ends up looking like this. Okay, so what we see here is an example of what this particular piecewise function could possibly look like. Okay. Our goal is to find values of a and b so that this particular function would actually look something more like this. And I'm going to use a different color to draw in what we want. So here, this piece, we would like for this piece to be connected here and go up like that. And this piece here, we would like it to come down here and look like that. And so the process that we're going to go through is going to say, hey, let's pick A and B such that these two pieces here connect with this piece here so that the function is essentially continuous everywhere. So that's really the idea of this particular example. Now, what we're going to do is we're going to computationally figure that out, meaning figure out what A and B should be so that if we wanted to draw the graph of this piecewise function, we would know what A and B would have to be in order for it to look something like this. Okay. All right. So now that we understand conceptually what's going on here, I'm going to erase this and then we're actually going to work out the problem computationally. All right. So to begin this problem, the first thing that we understand here is that in order to have each piece of this piecewise function sort of hook up so that it's going to be continuous everywhere, we know that the behavior of each piece is going to have to be the same at the x values for where they trade off what they act like. So for instance, at x equals 2, we know that this piece and this piece is affected. So in order for this particular function to be continuous here, we know that the limit as x approaches 2 of this function is going to have to be some number L here, okay? It's going to have to be the same. Now, to put that another way, since we have a piece that's to the left of x equals 2 and a piece that's to the right of x equals 2, then we're going to have to say the limit as x approaches 2 to the left of our function, f of x, which is going to be this x squared minus 4 over x minus 2, that has to be equal to the limit or the behavior of the function as x approaches 2 from the right of our right piece, which is this quadratic function, okay? And so what we have to do here is actually figure out, all right, well, what would that actually be? But this is one condition here, okay? The other condition that we have is at x equals 3, we have a trade-off in what the function acts like again. So here we would have to say limit as x approaches 3 to the left of this quadratic function is going to have to be equal to the limit as x approaches 3 from the right of our linear function here. Okay. So what we have to do is figure out what these two conditions are going to have to end up being. Now, in doing this problem, one of the things that I need to make clear here is that this step that I'm writing here and here is not an optional one. Okay. When you're doing problems like this, to state that the limit of the left piece has to equal the limit of the right piece everywhere where it trades off, you must write that step. You cannot skip that step. If you skip it, then you have the potential of getting points taken off on exams or whatnot, because if you just let this function here equal that function, or you just say, well, let me just plug in 2 here and let me plug in 2 here and go to work, then you have a situation where you're actually assuming something that isn't, okay? So remember here, we're actually, when we put this limit on here, we're talking about the behavior of the function, okay? And so we know that this x squared minus 4 divided by x minus 2, that expression is just going to simplify to x plus 2. But here, remember that this function is different than this one, okay? Remember that this is a line with a hole in it, where this one is just a line. But we know that at x equals 2, the behavior of these two functions are the same. Just because the function is acts the same at that x value doesn't mean that the function is the same at that x value. And that's why we got to have the limit operator thrown in there in our first steps here, okay? So I'm just going to go ahead and write this out now, and we'll just keep this as is for now. So we have this, and of course on this side, there's nothing else for us to really simplify here. So for this one, we see that we have a quadratic function, which is a polynomial of degree 2. So we can use the direct substitution property here and just plug in 3, okay? And we have to do this step first before we plug in the 3 into the values, into the place for x. So here this would be a times 3 squared minus b times 3 plus 3. And same deal here. This is a linear function, which is polynomial of degree 1. So we can use direct substitution property there. Okay. All right, so coming back to this one, kind of working these simultaneously here. At this point, we have the same situation that we had here. So I can use the direct substitution property. And same deal here. And so if I keep on going here, this will be 4. This will be 4a minus 2b plus 3. And then if I subtract 3 from both sides here, what I'll have is just 1 is equal to 4a minus 2b, okay? And so what you're starting to see now is that I have one equation where I have two unknowns. So if I want to know what a and b are, I'm going to have to know a second equation with two unknowns, and I'll get that from here. So this will be 9a minus 3b plus 3 equals 6 minus a plus b. And here we'll subtract 3 from both sides, add a to both sides, and subtract b from both sides. Of course, if we do that, all that cancels to 0, and we just have 3 here. And on the right side, we have 10a minus 4b, and those 3's cancel. So this is our second equation. And so now that we have two equations, two unknowns, we could use system of linear equations to solve this particular problem. And you could use several different methods if you want. I'm going to choose to use the elimination or addition method just because I think it'll be the easiest here for me to do. So here I have 10a minus 4b equals 3, and this will be 4a minus 2b equals 1. And what I'm going to do here is I'm going to multiply the bottom equation by -2. So if I do that, bring it over here, then what I'll end up having is 10a minus 4b equals 3. And then this will be minus 8a plus 4b equals -2. And that cancels. We have 2a here. This is 1. So a ends up being 1/2. Okay. Since we now know what a is, we can either use equation 1 or equation 2 to figure out what b is. I'll use equation 1. So here this will be 1 is equal to 4 times 1/2 equals 2b, which is 1 is equal to 2 minus b. and subtract 2 from both sides, you get a -1. And here you get a -1 divided by -2 equals b. So that means b is also 1/2. And so thus the answer to our question, which is what are the values of a and b that make this particular function continuous everywhere, it will be when a and b are both equal to 1/2. All right, so with this example, this concludes my discussion or my video on continuity and how it's defined in terms of limits and how we actually use that definition to be able to do some applications and examples. So I hope this video helped to clear things up on this concept. Look forward to seeing you in the next video. Take care.